The recording has started.
Okay. So hello everybody, my name is Tamer Farizovic and welcome to the last edition of the point distributions webinar for this year. Again, as usual, after the talk, there will be some time for social interactions, so please stay tuned or stay with us if you like. Our today's speaker is Laurent Bétermin, and he will be speaking about theta functions, ionic crystals, energies, and optimal lattices. So please, Laurent, the screen is yours.
Okay, thanks Damir for the introduction, and thanks the organizers for this very interesting and good opportunity to talk about point configuration. It's great. Yeah, so I will talk about this some optimality of ionic crystals. That's based on work with Markus Frühluber and Hans Knüpfer. But before, we have to celebrate today because it's a Pythagorean theorem day. We are the 12, 16, 20, and if you do a 12 square plus 16 square, it's equal to 20 square. Anyway, that's very important. The next one will be in 2025. So yeah, so I learned that this morning. I just add the slide. Yeah, 20 minutes ago or more, a bit more. Anyway, so the motivation of this work, and what I will present in this talk is from classical physics. So basically the idea is to justify in a way the existence of ionic crystals that will be classical solids, because I will take pairwise interaction potential here. There will be no quantum effect whatsoever, just something very simple, and I will show you that even in a simple case, of course, we all know that it's extremely difficult to solve. In particular, I would like to speak about this rock salt, so this sodium chloride structure as a ground state of some energy. So here you have a nice picture of a chloride, sodium chloride structure, okay, with this alternation of blue and green ions that are chloride and sodium, and that's exactly the zoom of what you see here. It's on a grain of salt, and of course, as usual, let's say that will be a minimal energy approach, and which is a bit here, a bit hidden. It's this connection between the potential energy, the potential interacting potential, and the minimizer of your energies. Okay, so just a few words about the mathematics of crystallization only for pairwise potential. Yeah, usually the goal is to determine the minimizer of this kind of potential energy, so the sum of pairs, and possibly when you average as n goes to infinity, so you take the thermodynamic limit and you ask yourself what is the minimizer of your energy. And for example, for the energy potential, we know that the triangular lattice is expected to be a ground state in the sense of the thermodynamic limit, and that's still an Opal problem in 2D, and that's just for the same kind of atom. So here I will talk about, so during this talk, I will talk about multi-component systems. So of course, if we are not able to solve this problem, the one I will explain will be extremely difficult to solve in the general case. So in the case where the particles are free. So for this kind of potential, let's say decreasing, increasing, only few results exist, but in particular, the triangular lattice is shown to be the global minimum if you take a sticky potential or a soft potential, but short range. Or we have this paper by Tile in 2006 showing that if something is a bit like that, but very narrow well, so decreasing, increasing, yeah, so you can show the optimality of the triangular lattice in that case. And we have adapted recently with De Luca and Petrake these methods for the square lattice. Right? And of course, which is important in this community of mathematical physics and optimal point configuration is this Wigner conjecture for Gelium. So basically, in dimension 2, you expect if you take a Coulombian interaction between the point and they are in a bath of, let's say, opposite charges, you expect the crystallization to be at fixed density on the triangular lattice. That's also what happened in the Ginzburg-Landau vortices. In dimension 3, you expect the same on the BCC lattice for this particle that are free and then crystallize on this structure. And dimension 8 and 24, it was shown by a combination of Kohn and all his collaborator, proving the universal optimality in dimension N24, and combined with a paper by Petrake and Sarfati, that it's proven in dimension N24. So for multi-component systems and lattice optimality, there is very few results. I would just want to cite a few of them, some of them. So there is this paper by Radin in 1986 where he showed quasi-periodicity in 2D for short-range interactions. These two papers by Friedrich and Kreutz in last year and this year, showing the optimality of honeycomb lattice or a square lattice with alternation of charges. So the particles are free, but you have two kind of interacting potentials, one for the same kind of charge and one for opposite charges, and then you get you get this alternation of charge. Some other result by Bouman, Dreisma, van der Valorten with the distance graph, which is a bit different. Something we did with Hans Knüpfer and Florian Nolte was published this year, but it's 1D case, so we have different kind of particles, different kind of potentials, and you can show the optimality of the equidistant configuration. And more recently, there is these two papers by Luo and Wei about free block copolymers and two-cobordant Bernstein condensates, where they show the optimality of some lattices when you fix the structure to be a lattice, and when you move you optimize among lattices. That's basically what I want to talk about, not about this paper, but something a bit related. And a recent paper I wrote about minimization of lattice energy with prescribed charges. So something that actually could come after this talk, because it's not, it's based on the result of this talk. And of course, there are many numerical investigation, and so I don't want to talk about that a lot. There will be some in 2D in particular, you have many of them, and I will show you some of them. Okay, so for more reference, you can visit the crystallization page I did. We will have a list of papers about crystallization and optimality of lattices. Good. So I did this talk last week, and I wrote like a small introduction about what lattices are, interaction potentials in that case, and charges. Of course, lattices, you all know what it is, discrete set, an infinite discrete set of this form. So L is the sum of the UI, where U1, UD is the basis of RD. Okay, so when I will say lattice, I will say that. So that will be something you can call Bravais lattices if you want, but that's, I will call it lattice. And so the set of lattice of dimension D will be written like LD, like that. And when you fix the volume, that will be written LD of V. Okay, and the dual lattice, as defined, as usual, is this set of points such that the inner product with the point of the lattice are integers. So the examples are very, the example I will give you here are very well known. The square lattice, which is E2, the triangular lattice. So here is with density 1, this lambda 0, I don't tell you what it is, but it is this lattice. So one point is surrounded by 6 neighbors all the time. So you have something called orthorhombic lattices. So the orthorhombic lattices are the ones that are generated by orthogonal vectors. So the basis of so that's the dilation of ZD, if you want, so in different orthogonal directions. So like this one. And the BCC and the FCC lattices, like, okay, body centered cubic and face centered cubic. The body centered cubic is here. So body centered because there is a particles, let's say, point in the middle of the cube, and face centered because the faces of the cube are also counted here. And of course, in dimension 8 and 24, we have these two best packings that are E8 and the Leech lattice lambda 24. Okay. And last thing to have to know about these lattices so far is that the dual lattice of an orthorhombic lattice will be orthorhombic as well. Okay. And the dual lattice of a triangular lattice will be a triangular lattice, just a rotation of it. And these two guys are a dual lattice to each other, as you may know. And you have also this fact that if E8 at density 1. So I will talk about density 1 all the time here. It's self-dual as well as the Leech lattice. That will be important at some point in the talk. Okay, so what kind of pairwise interacting potentials I choose? So during all this this talk, I will sum the energy on the square of the distances. Okay, that's why you have you will see some you will see some dimension divided by 2, but that's just that's just a technical problem. So I will consider interaction potential that are the Laplace transform of a measure. Okay, so that can be written like that. A particular case is when the measure is positive. So we know that it's a completely monotone function. So meaning that the derivatives of the function are alternating signs. And that's due to Bernstein. And a typical example of such potentials is the inverse power law. Okay, so all these inverse power law, you can written them like Laplace transform of this. Okay, this measure, which is positive, of course. And the whole strategy of what I will explain here is very simple. Okay, the basic strategy is very simple. The rest is less simple. But we use this representation as a Laplace transform as usual to write the sum of f. So when you sum the square of the distance, like the integral between 0 and plus infinity of this sum of Gaussians. And this sum of Gaussians is a kind of theta function. Okay, so of course here I remove 0 because, for example, for the inverse power law, it's not defined, but that's basically the idea. The idea is if you know things about the theta function for any value of the parameter t, you know the things about the energy when you sum f. Okay. So I wrote for suitable f. That means that just because I want to exchange this integral with this sum, so let's say that here all this f I will talk about, they will be absolutely summable. So there is no problem whatsoever of integrability. Okay, now I want to talk about charges on the lattice. So you have a lattice which is fixed, lattice L, and the distribution of charge is just the function from L to R, which gives you a number at each point of L, right? And I will assume that my distribution of charge is periodic. So it's n-periodic, meaning that it's periodic in all the direction where the cube, the periodicity cube, has size n times n times n times n, etc. Okay, so n at the power d point. So that's exactly what I see here in dimension 2 with n equal to 4. I have one periodicity cube, and then I write all the same thing everywhere by periodicity. Okay. So the periodicity cube is given by that. There is nothing to understand really here. And the total charge on the periodicity cube will be fixed. So the L2 norm of the charge will be fixed to be n at the power d. So just the idea is that when you take alternation of charge -1 and 1, you will find exactly that. Okay. And I will write Kn star, so the periodicity cube star for the same cube but in the dual lattice. So I have the lattice, and then I compute the dual, and then I have a new k and kn, and that's Kn star. Of course, to define that, I have to choose my basis in a certain way because, as you will see, it's you can get things that are completely different. So you have to choose a Minkowski radius basis, so that you have to choose this basis, for example, dimension 2, that allows us to write everything in the fundamental domain of lattices. So basically, you choose a basis on L such that when you take one vector ui of this basis, it's the smallest possible among all the other vectors, such that you can complete the basis to get another basis of the same lattice. Okay. So yeah, so in dimension 2, it's easy to state. So for example, let's say in any dimension, the Minkowski basis of an orthorhombic lattice, that will be the orthogonal one, the usual one, right? So there's nothing to understand here. In dimension 2, if you do that, you will have that U1 is less than U2 in norm, and the angle between U1 and U2 is between pi over 3 and pi over 2. Okay, the usual thing. And so that's a good definition for alternating charge distribution and for the center of your unit cell, right? So for example, here I have exactly the one we expect. So I take the square lattice and I take these two vectors. So the center of the cell is the one you can imagine. And the alternation of charge +1, -1, or plus minus plus minus is the one you can imagine when you choose like a 2D sodium chloride, right? But here, if you can do it, you can do something else. You can take this basis, right, which is not a reduced, Minkowski reduced basis. But now, if you take an alternation of charge on this lattice, you will have these lines of charge plus and minus. That's not what you want. And the center of the cell will be just the midpoint of one, let's say, vector here. So that's not what you want. So you want something on the left, right? Because to have a natural choice. So during the whole talk, when I speak about lattices, that will be a lattice with this basis and charge as well. Okay, so just a few words about the theta function. So the translated theta function, that's just a Gaussian where you sum over all the points of the lattice and everything is shifted by z, by a vector z on Rd, okay? And that's up to some renormalization. It solves the heat equation on the lattice. Basically, so this PDE, and with the initial condition is that at t equal to 0, you put sum of Dirac, so you put your temperature, so the same amount of temperature everywhere on your lattice. And something related to this translated theta function is this Poisson summation formula, but for Gaussians here, I don't explain it for more, but that's something you also know. That for any value of the parameter alpha, for any lattice of density 1, so here, and for any z, you have this formula, which means that the translated theta function is equal to up to a certain number of this sum on the dual lattice with this exponential, this complex exponential times also a Gaussian, but the parameter is reversed, and this exponential function plays the role of charge for me here. It's not that here it's complex, but when it's real, it will be a charge. Okay, so two types of optimality for this lattice theta function before showing some results. So you have two cases. One case, you put z equal to 0 and you optimize among lattices of fixed density. And the second case, you fix L, the lattice, and you optimize among the shifts, all the possible translation. So the first case, we know that so you have to fix the density, otherwise there is no minimizer for your lattices. And dimension 1, you have all result by Fente-Vogel, that for any alpha, so for any value of the parameter alpha, the equidistributed lattice z is optimal. Okay, it's even true for among all the periodic configurations. In dimension 2, it was shown by Montgomery that if you fix alpha, the triangular lattice will minimize your theta function. So that's a very important result in dimension 2. In dimension 3, you have only conjectures and numerics and some local optimality results. But basically, you have BCC. The minimizer will be BCC for alpha less than 1 and FCC for otherwise. And there is a phase around 1 where there is coexistence of the two phases. And in dimension N24, we know what I explained before by this result by Kohn, Kumar, Miller, Rajenko, and Biazowska last year, that the E8, the lattice E8 and the Leech lattice are both minimizer of this theta function, but also among all the periodic configurations. And the second part, there is less results. So now you fix the lattice and you play with Z. For d equal to 1, it's easy to show that the center of the cell is the minimizer. So if you have an orthorhombic lattice, so you fix L to be an orthorhombic lattice, then the center of the cell, defined for this Minkowski reduced basis, is the unique minimizer as well. And so that's something we showed with Mircea Petrake 3 years ago. And in 1997, Bernstein showed that the barycenter of the triangle, primitive triangle, is a minimizer of the theta function. So just to show you a picture, in the orthorhombic case, so in 2D, it's a rectangular case, the center is a minimizer, and in the triangular lattice case, you have two minimizers that are the bicenters. Very good. Okay, so now I want to talk about this first paper, Born's conjecture. So I already presented these things several times. Maybe you already have seen it, but so if you were at Braun Institute like a long time, I don't remember when it was, but 2 or 3 years ago, that's something I presented. But I want just to talk a bit about it. So that's a paper we wrote with Hans Knüpfer, and that's about a conjecture that Born stated in 1921. So Born asks the following question in German. I won't say it in German, but this paper was in German, and he asked how to arrange positive and negative charge. So well, a lot of charge in general on a simple cubic lattice. So you fix a lattice which is simple cubic, such that the electrostatic energy of your whole infinite crystal is minimal. So everything is fixed, and yeah, so that's, and you want just to play with the charges. Okay, so basically what Born conjecture for the Coulomb potential. So the interaction here, when you say electrostatic interaction, is Coulomb, right? So what he says is that the alternation of charge, so phi plus minus, of charge plus minus 1, so the one corresponding to the rock salt structure, is a unique solution among all the periodic distribution of charge, meaning that among all these charge as they are I've defined before, and all the possible value of n of the periodicity. So that's what it is written here, so depicted here. And of course, to show that, you have to assume that the total amount of charge is fixed, as I explained before, the L2 norm of the charge is fixed. And you also have to assume neutrality, so meaning that on a periodicity cube, the sum of the charge is 0. Because yeah, your Coulomb potential is not summable, so you have some problem of definition of the energy in that case. And Born, he proved that in 1D, and he proved the local optimality, the local minimality of the rock salt structure in 3D. And we follow his path, and the idea was to show this result, but in more generality. So that will be the only technical slide here, so the only computation, let's say, but I wanted just to show you what's going on when F is absolutely summable. So here I don't take Coulomb, but I take something easier, decreasing to 0 at infinity pretty fast. And I assume that the measure of associated to my F, to my potential, is positive. So I take a completely monotone potential. And now I want to use some discrete Fourier transform methods. Okay, so everything is hidden here in these two lines, but yeah, just read the paper or ask me if you want more information. But so the energy we define, so L and F are fixed, and phi is we optimize on phi, so it's varying. And what we do is we take the limit. So we take the limit if it's not absolutely summable, but I wanted to show you the Wolf energy first. So what we do is we renormalize just to have an energy per point, and we take the interaction between all the points of the lattice and all the points of one period, Kn, and we multiply the charge at y and at p plus y, okay, and then we take the interaction between p plus y and y. So when we do p plus y minus y, it's p. So that's why it's p squared here. And we multiply by Gaussian factor here. So just to define, to have a proper definition of the energy. So if your function was not absolutely summable, you would have to use eval summation method, and that's what you want to do for this eval summation method. So if you do that, and then you have many steps, but at the end of the process, you find that you can write everything using inverse Fourier transform, discrete in this discrete setting, that this energy can be written as a sum for any k in the periodic cube of the dual lattice of Ck Ek. Okay, and Ck, what it is just up to a certain multiplicative constant, which depends on the number of points, in your cube, it's just the inverse discrete Fourier transform of the convolution of phi with itself. Okay. And the magic of that is that it's positive, right? Because we all know that it's true for the continuous case, it's true for the discrete case, even though I don't give any definition here, but it's positive. And now I can write EK. So what is EK exactly? EK is the sum for among all the points that are not zero of this exponential, complex exponential function times f. And of course, here we can imagine that using Poisson summation formula, it's actually the sum of f shifted, right? And now I use the fact that f is the Laplace transform for measure, and I write this formula. So I exchange the sum and the integral. And after all this process, I find that it's the integral between 0 and plus infinity, this number which is positive times this theta function. So -1, but everything will be actually positive here. D mu f, and d mu f is also positive. Okay. So yeah, so now I'm happy, because what does it mean? That means that if I know how to minimize this theta function, I know how to minimize EK, and then by a certain process, I will know how to minimize the whole sum. That's a strategy, right? So if you're able to find the minimizer of this translated lattice theta function, but where is this? So where do you have to find the minimizer? You have to find it in KL star divided by n. So you have to rescale KN star. So you have to take a sublattice of your dual lattice. So you have to divide by n here. And so if you are able to find the minimizer, and if it fits with 1 point of this sublattice, then you are done. You can reconstruct psi here in a very easy way. You just say that it's 0 everywhere except for your minimizer. And then you can reconstruct uniquely phi. I don't explain why here, but that's, you have to believe me. Okay, so that's also true for non-summable function, and if you assume that everything is neutral on the periodicity cell, right? Okay, so that's the whole strategy, and now I explain how to apply that to two cases, right? So now you can show Bound's conjecture basically. You take any completely monotone potential f, okay, and so if L star is orthorhombic, then you know that the center of the cell will be the minimizer, as I explained before, and that will be reached for a certain n0, which is even. So that's easy to show that if you just take you divide everything by 2, you will have the center will be part of the sublattice. And if L star is a triangular lattice, which is itself, I mean, the dual of a triangular lattice actually, you know that the bicenter is a minimizer, and that will be reached when it's a multiple of 3, because it's a bicenter, right? So you divide by 3 to find it. So now you have the answer, because if you know where is the nut, where is the minimizer of your lattice theta function, you can reconstruct psi, and so you can reconstruct phi. So the unique minimizer of your energy among all the possible periodic configuration, that will be for the orthorhombic case, the alternation of charge plus minus 1, so this one. So you exactly find what Born predicted. And that's true also for any dimension, that's true for any interaction potential f, which is completely monotone. And in the triangular lattice case, you will find a distribution of charge of this kind, which is of charge minus square root of 2 over 2 and square root of 2, okay, in the triangular lattice. And on the left, you have this rock salt structure, and on the right, you have this sodium sulfide layer. So that's a one layer of a sodium sulfide. Okay, so that was the first thing we did with Hans Knüpfer, and so actually then we met with Markus Froluber, and we decided to work a bit on that. So actually we started to work on the problem that I will explain at the end of the talk. And recently we showed this thing, which is another optimality result for the theta function. But here I will assume that all the charges are already prescribed to be +1 - 1, so they will alternate, as I explained before. So we choose alternation of charge. We choose a completely monotone potential as usual. And we know that we can exchange sum and integral. So if you know how to minimize this kind of Gaussian with alternation of charge, you know how to minimize this kind of energy. First thing to understand that there is no minimizer of this energy. When you fix the charge to be plus minus one, it's sufficient to just to take something. So you want a minimizer at fixed density, and then it's sufficient to take a very elongated thin rectangular lattice to have an energy which goes to minus infinity or to zero. Sorry, to minus infinity. Sorry. And so the problem is now to find the maximizer in the set of lattices with density 1 of this theta function. Okay, so if you know how to do it for this alternate theta function, okay, with alternation of charge and Gaussian interaction, you will know more things for any completely monotone function. So that's a kind of universal optimality that you are looking for. So equivalently, by Poisson summation formula, you want to maximize among lattices of the fixed density 1 this centered lattice theta function, meaning that you have shifted everything by the center. So if you take the center and you take this exponential, this complex exponential function I showed you before, the charge will be minus 1, 1, minus 1, 1, minus 1. Okay. So that's equivalent here. So that means that the minimizer, there is no minimizer, but that will go to 0. Anyway. Okay, so what is the result we show with Marcus Foluber? So for these two theta functions at fixed density 1, we show that the triangular lattice is a unique maximizer of these two functions, lattice functions among lattices of density 1 dimension 2. Okay. So that's a new kind of optimality of universality optimality result. So as a direct consequence, you know that the same is true for any completely monotone potential. And so that's this universal maximality result among lattices only here. And that's conjectured to be true in dimension 8 and 24 for E8 and lambda 24. Okay. That's the maximized structure. So the maximizer of the energy will be like that. So this is basically the unit cell, and the alternation of charge is given like that. And for the triangular lattice, you will see these lines of opposite charge, plus and minus 1, which are exactly like that. Okay. So so that is the maximizer of our energy. So just an idea of the proof, but of course it's long and we have many estimates. But the idea is, as Montgomery did in '88, to parameterize the lattice by a point in the half elliptic domain here, this blue one, and you show that basically the function is increasing in that direction, so in the x direction, and now you are in for x equal to 1/2. That is the limit of your domain D. And you show that on this line, this theta function is decreasing, so in that direction, for a while between square root of 3/2 and plus infinity. So that's basically the idea. And to do that, we use estimates that are comparable to the one done by Montgomery in '88. Okay, so now we know that if we fix lattices, we know how to find the optimal charge distribution in some cases, okay, not in all the cases, but we have a strategy at least. Okay. And we know that for the alternation of charge, the square lattice or the cubic lattice is optimal in that sense, but the triangular lattice is maximal, so you have a lot of optimality results. And now I want to talk about this last paper we did with Marcus Foluber and Hans Knüpfer. On the optimality of the Roxa structure among lattices with charge distribution. That's something that has been accepted in mathematical model and methods in applied sciences recently, very recently. Okay, so now, of course, in reality, so when I explained Born's conjecture, what I did is I fixed the structure. Okay, so I fixed the structure and I play with the charge. But of course, if you, as we have seen before, if you shrink the lattice, you can show that there is no minimizer for this part of the energy, right? This charge interactions. So physically, what you want to do is you want to add repulsion at 0. Because if you have add a repulsion at 0, that will not allow your particles to be too close to each other, and then you will have a problem that will be very well defined. Okay, so that's what we do here. So now I call F a new one, which is F1 plus the product of the charge F2 of the differences. So the first part, F1, will be a repulsion at the origin, and the second part will be the tail of the interaction potential, but also the interacting charge part. Okay. And for this talk, so in the paper we have also studied Gaussians. Okay, but here I will talk only about inverse power laws. So F1 will be 1 over R to the power P, and F2 will be 1 over R to the power Q. And P and Q will be such that everything works well, everything will decrease at infinity to 0 fast enough to be absolutely summable and to inverse this integral this as usual. So P is larger than Q and larger than D over 2. Okay. So that means that you have, for the same kind of particles, you will have a decreasing potential. And for opposite charge, you will have something which is decreasing and increasing as interactions. Right. So the new total energy per point is given by this energy per point for F1, so the sum of F1 over all the square distances on the lattice L. And the second part depends on the lattice and on the charge distribution. That will be the product of the charge times F2 of the distance. So that's exactly the things I explained before, times 2, because I didn't divide by 2, because here I count twice all the pairs. Okay. And now the question is well posed. So the question is the following: can we find the minimizer of this energy, EF1, F2, among all the possible lattices without fixing the density and all the possible charge distributions? So that's a very difficult problem, the very general problem. And the second question is that the Roxa structure, this minimizer? Okay, so is that a natural object which minimizes this energy? The answer seems to be yes, but of course many things, that what I'm going to show you are like these first results in this direction, but that's already showing interesting things. Okay, so first I just speak about these two competitive energies just to tell you what's going on, because I just explained it before, but it's also, I just want to add things to more information. Okay, so you have EF1 and this second energy. Okay, so for now I'm talking about the first part. So the first part, if mu F1 is positive, so if F1 is completely monotone, then we know what's going on, more or less. Of course, we don't know in all dimensions, but it's equivalent with the theta function problem. So EF1 has a minimizer if you fix the density. Okay. In dimension 2, it's a triangular lattice, we know. In dimension 3, it could be the BCC or the FCC, probably changing with V, as it is the case for the Gaussian. In dimension 8 and 24, we know already that it's A8 and the Lich lattice. Okay. And an important case is that among orthorhombic lattices, the cubic lattice, so here there is a factor V 1 over D, but that's the volume of the cell, and that's just the one you have to put to have a lattice of volume V, okay? And so among orthorhombic lattices, the cubic lattice is a unique minimizer of the first energy among lattices of fixed density, okay, 1 over V. So if you fix the volume equal to V, you have the cubic lattice, which is a unique minimizer. So that's something Montgomery showed in his paper. So in his paper, there is this optimality of the triangular lattice first, and then there is a small theorem somewhere at the end of the paper, I think, or no, just at the beginning, but it's proven at the end of the paper, and that's exactly what he said. And now the second part. So I still choose F2 to be completely monotone. I know that there is no minimizer, there is only maximizer. In dimension 2, I know that it's a triangular lattice, but otherwise I don't know. But if L is fixed, I have the possibility to find the optimal distribution of charge. That's what I explained at the beginning of the talk. If phi equal to 1, then this one and this one are the same basically, but here it's for F2 and this one is for F1, okay? But it's of course not optimal because it's everything, I mean, F1 and F2 are positive. So of course, if you take only positive charge, it's a bit stupid. It's enough to put one negative charge somewhere to change a bit the energy. So that won't be optimal, but at least I would know how it works in that case, but it's not interesting. And if I choose the charge to be plus minus 1 here, then the triangular lattice is a unique maximizer. That's what I explained in the second part of the talk. And among orthorhombic lattices, there is a result by Folluber, Einstein, and Berger, showing that if you are in the orthorhombic lattice case, and if you alternate the charges, okay, the cubic lattice is a unique maximizer of the energy. So that's a unique maximizer, whereas for the first energy, it's a unique minimizer. So that's two things that are like competitive behaviors for this in the orthorhombic case and in the non-orthorhombic case. So you are really a symmetry of opposite behavior for the triangular lattice and the square lattice, basically, for example, in dimension 2. Good. So now I want to present something. So a result we obtain, so a rigorous result to obtain. If you fix the structure to be orthorhombic and you fix the charge to be plus minus 1. But of course, so the first thing that we know is that if I'm orthorhombic, the best optimal, so the best distribution of charge I can put on my lattice is a plus minus charge alternate configuration. Okay, so for orthorhombic, it's fine. I can just focus on the plus minus charge because it's already optimal. So that's what I wrote here, that this energy, which is for the plus minus charge, is always less than any energy for any phi, right? And so that's why it is an interesting case, because now you don't have to optimize among charges, you just have to optimize among lattices. So that's the result, one of the results we obtained with Markus Folluber and Hans Knüpfer. And so I choose two inverse power laws I explained. So the first thing that we can show is that the cubic lattice of volume V is a critical point at fixed volume V of this energy for any F1, F2 actually, not only for this one, but for any F1, F2. The second thing I can show is that there exists volume V naught, such that for any volume between 0 and V naught, so at very, very small volume, the unique minimizer of my energy, it will be, donc among all the orthorhombic lattices, because I fix L to be orthorhombic, will be a cubic lattice. So at very, very high density, I can get as a global minimum a cubic lattice. Okay, but at high density, and this V naught is not explicit. I have to admit that it's almost an asymptotic result, but there is a V naught which is finite, such that it works. And there is a volume, so when the volume is too large, so at low density, such that the cubic lattice is not a minimizer if you fix the density V among orthorhombic lattices, so it's not even a minimizer among all the lattices. But the take-home message here is this one. So if you restrict to orthorhombic lattices, the Roxas structure is globally optimal among charges and lattices at high density. So if you fix at high density, you will get the Roxas structure. So now if you imagine that your orbitals, so you are on a crystal and you have also orbitals, they force you to be in a certain orthorhombic shape, then you can know what will be the minimizer at high density. And now, okay, so the idea is, okay, what about not restricting to these orthorhombic lattices? Then you can do something. So there is something that we call alternate Epstein zeta function. So that's Epstein zeta function, alternation of charge here divided by the distance at the power s, okay? And so what we know already is that this guy, because it's alternation of charge and the potential is completely monotone, is that all these values are negative. So that's something we know in dimension 2, but that's something we ignore in higher dimension. At least we don't know how to do it. But that's expected to be true for in any dimension that this value is negative. So in that case, I can compute the minimal value of the energy among all the deleted of one lattice L of density 1. So I have one lattice L of density 1, and then I play with all the deleted, and that's a one parameter question, that's one parameter problem. So I know how to minimize it. It's not difficult because it's a decreasing, increasing function. And so there is a value for that. Okay, so that's a value which depends on the alternate Epstein zeta function and on the Epstein zeta function itself. I know how to compute that. And now I have, so I had, for example, in dimension 2, I had a dimension 3 problem. So you have 3 parameters if you don't fix the density for the global minimum among all the possible lattices. And now you have only 2 parameters. So you are happy, so you can plot things, you can do something interesting. So the question is, what is the minimizer of this quantity in the space of lattices of density 1, now that everything is well scaled? And if you take, for example, R-8 and R-6, so P equal to 8 and P equal to 6, you can make this nice plot in dimension 2. So that's the half fundamental domain that's of lattices that, as I explained before. And the minimum, so the blue part, is exactly here. And that's exactly the point that corresponds to the square lattice, meaning that for my energy with alternation of charge, the global minimum should be a rock-side structure, a 2-dimensional rock-side structure. Okay, that's what you see here. And we did a lot of experiments with other parameters. It seems to be true, except for some cases that I will explain in a few. But yeah, so we also did some computation dimension 3, 8, 24, and actually in dimension 8 and 3 more precisely. And we have compared different values, and it seemed to be also the case. But of course, we are far to claim that it's true. Here you can see that it's true. It's not a proof, of course. So when you compare all this energy, I mean, the thing is that we never saw any structure with lower energy than the rock-side structure. Okay, even if we take optimal charge distribution, use, for example, for the Born's problem, you can compute for the triangular lattice the optimal structure. Even for this structure, you don't find something which is lower. And another thing which is interesting, and I really like this thing, is that when V increase and you choose this energy with alternation of charge plus minus 1, you see a funny phase transition. For V very small, you say that the triangular lattice is actually the minimum. Okay, so it's due to the fact that the first part of the energy is minimized by the triangular lattice. And then when V increases, the minimizers is a rhombic lattice. So at first it was a triangular lattice. Now it's a rhombic lattice. So the angle is a bit larger than 60 degrees. And then it moves a bit like that continuously until to be a square lattice when it stays a bit. So now it's a square lattice. And now if V increase again at fixed density V, but at fixed volume V, you becomes elongated, more and more elongated rectangular lattice. So that's something we already observed in the Lennard-Jones-Morse potentials case, and that's something also observed in the free block copolymer and Bose-Einstein condensate case by Lu and Wei. So they also proved that, and it was also observed. And the last things about this experiment I want to say is that if P and Q are too close to each other, then the minimizer is not a square lattice. So it does not work anymore. So if the two potentials are too similar, something weird happened, and it's not the square lattice anymore. It's something like a rectangular lattice, or these things are moving. But that's not the square lattice. So you can do the same picture as here and show that it's not the case. Okay, conclusion of this talk, because it's time to conclude. So 3 parts. 3 different things. So the first part, we showed some new general strategy to optimize energies among charges on a fixed lattice. And the key point is to minimize the minimization of this translated lattice theta function. Okay. So if you know how to minimize that, you know how to reconstruct the signal, let's say the charge, which is a kind of signal here. And the second part, we show a new universal optimality property for the triangular lattice, which is a maximality property. And the key point is the maximization, not the minimization, but the maximization of the alternate theta function. And the last part, we show a new type of minimization problem for ZD, which is a bit different. So now keep in mind that when you don't have the same kind of, when you have the same kind of particles, what you expect is more like a base packing. It's not true, but basically that's you don't expect really the cubic lattice to be a minimizer of your ground state, right? But here, when you put charges, that's the situation is quite different. And what we have seen is some cases where we can show that the cubic lattice is a minimizer, and in particular the rock salt structure is a ground state of our energy. And when we restrict to plus minus charge, it's similar to minimizing something which is of the same with the same kind of particles plus something which with alternation of charges, okay, with alpha and smaller than beta. So that's something a bit similar. And I would like to thank you for your attention, and yeah, thanks a lot.
So we thank you for this very nice talk. So thank you. Now, questions. So please feel free to ask anything you like. You can use the chat or just unmute yourself.
Is it something in the chat? Okay, that's just.
So I had a question. So around the middle of your talk, you were relating these theta functions to solutions of the heat equation. I think that's the first time I've seen some relation to like a partial differential equation for anything like this. In any other, I guess, do you know of any other instances where work like this on the lattice has been connected to other really well-known differential equations?
No, I have to admit that no, but that's a good question, because that's a very important thing, because this heat equations is used by, for example, Bernstein when he studies the optimality for the triangular lattice, and he's looking for the minimizer of among all the z possible, right? If you remember, he used this the property of this heat equation. So that's a very important thing, because he uses that. And there is also a recent paper by Stefan Steinberger where he used also the heat equation. That's a bit related to this kind of crystallization problem. So there is some connection with the sphere that you can do, but yeah, that's something. Yeah, but otherwise I don't know anything. The point here is that, of course, you use the fact that it's a Gaussian, so you know that the Gaussian is a solution of this PDE. So that's why it arises, but otherwise I don't know. No, I have no idea right now about another PDE for that. But yeah, that would be interesting, because if you know another PDE, you will want to use the properties of this PDE to say something about the critical point or whatever. So that's very important. Yeah.
Okay. So thank you. Any more questions? Yes, I guess there were competing opinions. Okay, Alex, please go on.
Okay, great. Thank you, Laurent, for the great talk. So just to make sure I understand correctly, so all of these minimizers, they always have alternating charges. So it's always the two nearby charges have opposite sign, right?
Yeah, sure.
So yeah. Can you ever cook up anything? I'm just curious. It's probably silly, just a silly thing, but is there anything reasonable that would lead to adjacent charges having the same sign?
Oh, actually, yes. For example, I give you one example. So that's something which is not published, but anyway. So if you take the BCC lattice, so I'll just take the picture somewhere, just to be clear. So if you take the BCC lattice, you can show that the minimizer is given by charge plus minus 1, but all these points, so all these points of the cube are charge plus 1, and the charge in the middle is charge minus 1, which is, okay, these two guys are adjacent and have the same charge. I'm cheating when I say that because I understand your question and I have no example which will be better than this one, but yeah, that's the one I know. And that's also interesting because in that case, this structure, it's another kind of salt that exists in nature and in 3D. So that's also, it's not an happenstance. But yeah, otherwise I don't know any other solution of the problem with the same kind of charge next to each other.
Also, I'm curious if you looked at any of the more exotic dimensions. So they're obviously experts for this on this call, but say, have you looked at 4?
No, I mean not really. No. I mean, my point is okay. So okay. So So your question is that now I fixed my D4, for example.
Yes.
And I play with a charge on D4. No, so I didn't look at it. I mean, yeah, that will of course very interesting to do it. I agree, but I don't exactly know right now.
Yeah, I don't know.
No, I think, I mean, usually the good idea is to decompose your lattice as a layers of like cubic 1 or this kind of thing. And if you know how to do it, if you are lucky, you can your minimizer will be the center of the cell or something like that of this subcube you take, and then you can maybe conclude. But that's yeah, that's just a guess, and I don't know. But that's the usual way to do it. Otherwise, you can maybe try to do this heat equation techniques, but of course, in dimension 4, it's quite difficult to imagine everything, and I don't want to.
Right, exactly.
Something horrible. Yeah. I don't say it's easy. That's my point.
Yeah, exactly. I see. Yeah. Thank you. And there was this numerical. Other numerical observations slide. So could you clarify? So you say that the same transitions have been observed for all these other potentials. So is this literally the same transition? So as you grow the density, exactly the same transitions apply to these other potentials as well.
Okay, so yeah, so that's exactly the same qualitative thing. Not, of course, the value for the transition are not the same, but that's exactly the same qualitative thing. So if you take so if you choose, for example, the EF1, so yeah, so if I choose just EF1 here, I forgot the rest, and I play with V. And if I choose F1 to be a Lennard-Jones potential, so a difference of 2 inverse power laws, that's what I will observe. So that I will observe this change of minimizer from the triangular one for very small v, because for very small v, the first part is the one which wins. So basically just an Epstein zeta function, so it will win. And then when v is increasing, it changes everything about the behavior. So yeah, but that's for the most potential. That's what you see as well numerically, and yeah. Of course, for free block copolymers and Bose-Einstein condensate, that's the same kind of thing, but not with the density, but with some parameters. But that's the same.
All right, thank you very much. So, any more questions?
Yes, I have a question, Laurent. Nice talk, thank you. I have a question which maybe a bit more physical than mathematical. So you talk about this Lennard-Jones potential.
Yeah.
And sometime I read that the Lennard-Jones potential is considered like a 2-charge potential. Maybe I don't know if this means that that it's considered as a non-physical when applied to 3 or more particles, or is it considered just like a first approximation to what is supposed to be reality? Or do you know about that?
Yeah, that's more. I mean, that's the one which So you have this 12 and this 6 normally. So it's 1 over r to the power 12 minus 1 over r to the power 6. This 6 corresponds to the van der Waals force you have between neutral atoms. So normally it's for neutral, completely neutral atoms. And this 12 is something which has been chosen arbitrarily such that it's, I mean, things are working well when you compute, but that's good when you have a neutral, the same kind of particles, yes. Yes.
And if you have more than 2 particles, if they are neutral, still people would use that.
No, sure. Yeah, when they do numerical experiments, they use usually this Lennard-Jones potential is used widely used for numerical experiments.
Oh, great!
Yeah.
And it's still unsolved again, right? As you said,
Yes.
triangular lattice is not known to.
Exactly. This triangular lattice thing is not known. Even with the things I discussed before, I mean, the paper I wrote about this lattice energies and so on, you cannot apply these methods to 12 and 6, but to smaller parameters. But among lattices, for smaller parameters, for example, 4 and 3, let's say, you can show that the global minimum is a triangular lattice, but only among lattices. But for 12 and 6, there is no result in that direction actually. So it's already difficult to do in the lattice case.
Wow. So that must be a big open question in mathematical physics, right? Because that's their most important potential probably, right?
Yes, and if you read Tile's paper, and that's something which is far to be Lennard-Jones potential. That's something which is really increasing, but it is a very, very narrow well, and that's not a good approximation of this guy, which has a normal well, let's say. I mean, whatever it means, but this is more an approximation of the sticky disk than a real smooth, nice. Potential with a wide well, unfortunately.
Okay, great. And would you know, for example, these molecules that exist, which are like round, say, like these Buckminster figurines, they're figurines, they call them, right?
Mm-hmm.
When you have these carbon atoms.
Yeah, sure.
This is supposed to minimize a potential also. Is it
Yes.
Lennard-Jones potential too, or?
That I don't want to say stupid things, so
Maybe it's a completely freak question that just came to my mind.
No, I don't want to. Yeah, okay. So I know that in Kumar's paper they speak about that and they use completely random potential, but for this one, I don't know, because of course it will depend on the size of your things. But if the size is very, very small compared to the minimum of the potential, maybe you can expect that the first part of the potential will be the one which wins, which I think it is true because you are on the sphere. So yes, that should work. Okay, so I think it's a proof that it should work. Anyway, I mean, okay, I guess that should work.
Okay, thank you very much.
Possible?
Sorry?
If there's still time, I have a question. Is there a ternary version of what you're studying where you take 3 species?
That's a good question. We didn't do it actually.
Because underlying what you're talking about, there's a Z2 symmetry. Mm-hmm. So in some sense, what I'm sort of thinking is what happens when you break that and you go to a different symmetry group.
Yeah, that should change. I mean, yeah. So your point is that maybe, for example, to minimize something, as I explained at the last part of the talk, yeah, something like that, but with three species. Sorry, species.
Yeah.
And
that also relates to the previous remark about whether you have to go beyond a binary interaction.
Yeah.
So both questions.
Yeah, I mean, so now if you go to the ternary interaction, then that I don't really know. I mean,
it'd be super interesting. Do you know if there's any numerical work in that direction?
In dimension 3, I mean, in dimension 2, you have no. I mean, I don't know. No, I have to admit that I don't know. I think I saw it maybe in the paper we wrote some references, but I don't have it in mind right now.
Thank you very much. Great talk. Very interesting.
Thank you.
Any more questions? perhaps a silly one for me. So you said if P and Q are close to each other, right? Then things actually get weird. So just wonder, is this something that could actually happen in reality? Are there some potentials where P and Q are close to each other, which people actually use, where you can measure things? Or is this just a mathematical artifact?
I mean, for me, it's a mathematical artifact, yes. Because usually, I mean, even if the very first model, like the one studied in the last century, P minus, I mean, basically P was 2 and Q was 1. So, but in that case, you can show that everything works well. So I think it's more a mathematical artifact, but I think it's also an interesting thing because now if you simulate it, I mean, I don't know if you want to create a new ground state physically, maybe you can do it with that kind of potential and particles. So I don't know. But that's, yeah.
I see. All right, thank you very much. Now let's perhaps stop the recording and we go on for questions off the record and some more announcements.